be generated from dark matter like annihilation and pair production.
Quark can be produced.
Yeah, quarks will be a quark and anti-quark pair will be generated from
Yes.
right.
Yes.
I don't exactly understand how is that possible. Like we don't understand exactly what dark matter is, right? So how can we say that?
So this depends on the model of dark matter. This is not a model independent statement, but there is a very interesting model of dark matter called supersymmetric WIMP dark matter, where the dark matter are like 100 GeV heavy mass, and they have weak interaction. So there are certain allowed interactions which can be allowed, and few such interactions are like through weak interaction. That you see, quark interact through weak interaction. Okay.
Okay.
And so that's why they can decay. But it is not so straightforward to say that. You need to exactly, like it's called LSP, lightest supersymmetric particle. You need to study the supersymmetry and quantum field theory. Then they have exact channel that what are the channel dark matter can annihilate. So that we don't have scope in this class. But dark matter can interact weakly with standard model particles. That you should know. Okay.
Okay. So that
but still it is an assumption. Till now we have not detected WIMP. It is one of the model of specific model of WIMP. There are a couple of more, but we don't know which one it is. So these are all speculation. But with speculation only, we have to move ahead, because if we don't assume anything, then we cannot detect them. No, you have to assume that okay, this is a possibility, and then you detect. And if you detect, then you see that our assumptions is right.
Okay, sir. Okay.
Next class we'll talk about it a little bit more. Okay. So I think we'll start now. Whomever is here. So like that, we did this integral, and Jahan has sent me the homework. Also, he calculated the neutrino decoupling temperature by using the equation which I said last class. You should also do it. Send me in the weekend. So here we did N and rho in the last class, but pressure can also be done like that. Pressure is basically momentum square by 3E average of that with f of p dqp. To get an idea why pressure is like that, analogy. So pressure in relativistic fluid or relativistic particle is 1/3 mv square gamma. Okay, and you use here E equals to m times gamma. Gamma is the Lorentz factor. You know that. The E is m times gamma, and pressure is mv, velocity, times gamma. If you substitute this, you get p square by 3. Okay. So if you know momentum and energy, you know the pressure. So now if you put it here, this p square by 3 EP, 3 E is basically PC, we know, and basically you do the integral. You will also get the result, and with this momentum distribution function. So now I'm going to the main result, which I have not shown totally in the last class. Where is it? Let me go back. Sorry. Yeah. So for relativistic particle, relativistic boson or fermion, the difference between boson and fermion is where the difference will come? In the integral above. Suppose I want to do an average with a photon, or I want to do an average with neutrino. Where the main difference will come? Who can tell? Huh? Yes, yes. No, this is not. This is the integral. A for not energy. A for P. A for P. This is not energy. Distribution function has this difference. No. Minus is for boson and plus is for fermion. So if you do the same integral for photon, you get minus. For neutrino or electron, therefore they are in thermal equilibrium, you get plus. And once you do the sign change, you get a different zeta function, and that's why you get this result. Say, for example, here. So you get for number density of Bose-Einstein, you get just factor 1 times zeta 3 by pi square GT cube. Zeta 3 is 1.2. So you basically get 1.2 by pi square GT cube. G is the degrees of freedom. Okay. Rho, and for fermion, you get 3 by 4 because of the plus in the distribution function. You should do it, your homework. Okay. Zeta function. And rho, you get similar thing, 1 times pi square by 30. Here we have already used the zeta function, I think so. So pi square by 30, and that Jahan has already calculated, send me already, but you can do it, it is easy. Pi square by 30 g t to the power 4, but here you get 7 by 8. So for 1 degree, same degrees of freedom, say for photon has 2 degrees, g is 2 for photon. Okay? For electron also g is 2. Okay, so then g is same, or neutrino also g is 2. Okay, but their numbered energy density rho will be, which one will have higher energy density? Rho, photon or neutrino? Tell me. So it is already given here, no? Rho is the average of energy density, okay? Integral over f of p. That is what actually you observe, okay, rho in thermal equilibrium. So which will have higher energy, photon or neutrino?
Photon.
Photon. And neutrino will have little less, 7 by 8 times that of the photon, if the g is as same. Is it clear?
Yes, sir.
This comes from the Bose-Einstein's or Fermi-Dirac distribution function. It has nothing to do with. So now, and p, if you also do the integral with p square by 3, do it, and then you will see you will get 1/3 times rho. That you should prove it. This is also your homework. P equals to, by doing the integral. So then you know that exactly why we say W for radiation is P by rho is 1/3. You remember? We used W equals to 1/3 for radiation. Yes?
Yes, sir.
That can be exactly derived from this Bose-Einstein, or sorry, Fermi-Dirac. It doesn't matter, it's the same for this valid for any radiation, either photon or neutrino. That is your homework. Okay. And also in last class we show that rho is t to the power 4. You remember we did the integral by doing that. It is proportional to t to the power 4. Yes, we defined x as p by t and took all the t term out, t to the power 4. So, and then there will be a constant. So that constant comes as sigma. So you know from your previous knowledge of thermodynamics that for Stephen Boltzmann's constant is for radiating body, it is sigma in t to the power 4. Yes?
Yes, sir.
So here we derive it from thermodynamics and Bose-Einstein theory. We did it in the last class, sigma times t to the power 4. So now what we are going to do, you should remember this. You should remember this part very well. Okay, this n rho sigma for fermion and boson, and p equals to 1/3 rho. Okay. Now we'll be a little bit going in deeper with the G. You'll know what I'll be doing. Okay. Okay. So just remember this. Pi square by 30 g t to the power 4, 1 for boson and 1 for 7 by 8 for fermion. Okay, so now let me go back. So you tell me what was the rho? Let me go to a different color. How much? For rho boson thermal and rho fermion thermal equilibrium. What is this? No, you tell me, you should remember, no? 1 times
pi square by 30
times
GT power 4.
E into T to the power 4. Very nice. And for this one, it will be?
A 7 by 8 factor.
Then same. Huh?
Yes.
Very nice. G into T to the power. Okay, so now what happens in the early universe? Early hot universe. As I said, everything was in thermal equilibrium and just after Big Bang. All the particle means C. Quark is in thermal equilibrium with quark can interact, weak interacting or strong interacting. So quark forms basically atoms, and atoms can interact with electrons. Then electrons can interact with photon. Quark can interact with neutrino, because that's why the weak interaction comes. The neutron, proton is nothing but quark. So all these things, along with that, all quark, they are called this. And like that, there are also other particles, muons, tau particle. They are the leptons, and like that, there are 6 quarks: up, down, top. Charm, strange, and top, bottom. There are 6 quarks, and there are 6 leptons: electron, muon, tau, and electron, neutrino, muon, neutrino, tau, neutrino. These are the 6 leptons. These are the building block of matters in standard model. This part up and down goes into the quark. You know that, goes into the neutron and proton. Proton is UUD. Okay? Proton is 2 up quark and down quark. And neutron, anybody know what is made up of? You don't know, no?
1 or 2 down quark.
1 up and 2 down. Very nice. Okay? So up quark has charge plus 2/3, and down quark has charge minus 1/3. So 2/3 plus 2/3, 4/3, and minus 1/3, you get 1 charge. Okay? Here you see 2/3 plus 2/3, and these are like minus 1/3, and this is minus 1/3 charge. So total charge is 0 charge. You can see. And here proton, the total charge is 1. Like that, there are many particles in the universe. They are all in thermal equilibrium. Okay. So I don't need to do all this thing now. Just go to the thermal equilibrium. Okay. So now what was happening in early universe, all their temperature, when they are in thermal equilibrium, all the temperatures are same or different? You tell me. Thermal equilibrium, if they are in strong equilibrium with each other, they share the same temperature or different temperature?
Same temperature.
Exactly. So T for quark, T for electron, T for neutrino, all were same. All were same. Mainly quark, neutrino, photon, and electron. I'm just giving few. All have the same temperature. Now, as universe cools down, generally what happens, these equations is hit. Gamma of their reactions become H. And once that happens, the whole expansion takes over and they come out of equilibrium. They come out of equilibrium. So at different time of the universe, different things comes out of equilibrium. So I have shown you in last class that most of the time, most of the time, when a particle becomes non-relativistic, or their mass becomes heavy than the temperature of the universe, the decoupling happen, or in other words, it is also called freeze out. Same as decoupling, means they come out of thermal equilibrium. Freeze out happens. And that is true for most of the particle, like I have told, dark matter going to standard model particle, SM means standard model, and the reverse. You remember last class we did that? First they're like that, then exponential drop, and then they become constant. Yes, you remember? Yes. This happens, this freeze out happens when they are non-relativistic, and that's why we use the Maxwell's Boltzmann distribution, e to the power minus m by t, and exponential drop. Like that, we know that. So this generally happens when mass of the particle, say for example m pi, is a little bit higher than the temperature, or more or less m chi is close to, say, a few times temperature of the universe. Say I am telling 10 temperature. Example, just 10 or 15 is the number. So then the freeze out happens. This can be exactly solved. But you see that mass is higher than temperature, that means it's non-relativistic. Because when temperature is higher than mass, that means it's relativistic, because the momentum is high. So that is true also for other decoupling. This is example number 1. We give another example last class. What is that? Can anybody remember? Like dark matter, we did another one. Okay. What is that? E minus plus
E plus.
E plus going to gamma. Very nice. And this goes back. So this was in equilibrium, and when universe temperature comes closer to 531 MeV, that is the mass of the electron, and drops little bit below, then we see that the electron and positron number density freeze out like that again, like this dark matter, and they become constant. Okay? So like that, that's why we get some electron positron density. And those electrons, positrons, or those dark matter, they are out of thermal equilibrium. That means what? Out of thermal equilibrium means they now in their own zone. They are everywhere, but they don't interact with other. So from now onwards, they will not interact. At least with the photons like that, they will not interact. Okay, E plus. This channel will not interact. Okay, so it is true for any reaction. Thermal equilibrium and freeze out is for any reaction by reaction. You cannot say that they will not interact with anything else. No, this production of photon from electron and positron, it was going more and more. Electron number density was going down. That will stop. So that electrons will be found in the interstellar media and all these things. If it would continue, then we'll end up with no electron today or positron today. But these electrons, what is now decoupled, they also stay like that neutrino, whatever they decoupled, we show that it happens when universe is 1 second. Jaham has done the homework. When neutrino decoupling happened, 1 second, and neutrinos stay there, and they stay, but they have their own interaction. So they will not talk or interact, talk to other particle. So they are kind of secluded. Okay, is it clear now? When you come out of the cosmic soup, then you remain with your own territory. You are everywhere, but you don't interact with others. Is it clear?
Yes, sir.
So now, this rho, what we say, suppose there are fermions and bosons, both in the universe. So we have to do 1 times pi square. So this is the sum over boson, pi square by 30 into G into T to the power 4. Plus for fermion, it will be very similar, but what will be the change? Who can tell me? You have to sum over all the fermions to get the total rho of the universe in thermal, when they are already in thermal equilibrium. What will be the change here?
7/8.
7/8. Very nice. And then everything is same. This is G fermions and this is G bosons. So suppose I now have, so during CMB time, I tell you, this is just you remember now, during CMB time, only 3 particles are in thermal equilibrium within our universe. Okay. See, okay, let me tell you why I have to assume. I'll just show you a little thing. Then you will know that what decouples when. So let me just go to so now forget about that. So now suppose, for example, I have a system of equilibrium where I have 1 photon and 3 neutrino. Okay, and they are all in same temperature. So if there is same temperature, then what I'll do like pi square by 30. Then I'll take the T to the power 4 out. And then what I have is G bosons plus 7/8 G fermions. Okay. Now I am just giving you this. This G can be calculated from particle physics. You just know that G neutrino is 2. G electron, E minus, is 2. Similarly, G positron is also 2. Because in particle physics, every particle has left hand and right hand spin. So they are degrees of freedom. Okay. And G neutrino, I have already told. And G photon is also 2. But as electrons and positrons are both there, neutrino we don't have there. Neutrino and anti-neutrino, dono mila ke ye 2 hota hai. I will not go into the detail. Okay, they are sometimes called Majorana particle. You don't need to know. And photon is nothing called their antiparticle, or they are chargeless. So they are their own antiparticle. So that's why they are 2. But if you take electron and positron, then you have to add both 2 plus 2, 4. Like that for quark also. Quark, it is 2, anti-quark. For up quark, it is 2. For up quark ka jo antiparticle hai, that is also 2. For down quark, it is 2. For all the things, okay? For every particle in the fundamental particle, it is mainly 2. So now you tell me, if I have a system, if I have in thermal equilibrium or relativistic, for example, thermal equilibrium, 1 photon, then E plus and E minus, and 3 neutrinos. What will be this factor? This factor, sometimes we call it as effective degrees of freedom, which is the sum over everything. We call it G star. So what will be the G star? You tell me. For these 5 things, they are all in thermal equilibrium, for example. Can you calculate and tell me? It's very easy. So you have to choose which one is boson. Only one particle is boson, that is neutrino. That is photon. That has 2. Plus 7/8 times, for electron it is 2, for positron it is 2, and for each neutrino it is 2, 2, 2, 2. So it is 6. This is 6. So total degrees of freedom is thus 70/8. So what will be this number? Can somebody tell me? 10.75. Very nice. 10.75. So when in early universe, these are the only particles which remains in equilibrium, because see, quarks are heavy, they go out of equilibrium faster. So then what remains is neutrino, electron, positron, and photon. So that time, if somebody tells you, find out your Hubble's constant, H. So then you use H is equal to that equation that we have done in the last class, G star times T square by M Planck. There will be a factor in front. Okay, this is the equation of H in Planck unit from Friedman equation. You see, H is equal to H square is equal to rho, H is equal to square root of rho, and rho goes as T to the power 4. We have just done. You can also see here T to the power 4. So square root of rho will go as sorry, this is G star T square. So now here you have to just put. There will be a constant I forgot. I'll give you in exact notes. So it will be like you have to put G star as 10.75 times T square by M Planck. So given the number of particles in thermal equilibrium, you can calculate the expansion rate in the early universe. So now you see that how thermodynamics or the Bose-Einstein statistics or Fermi-Dirac statistics is telling you what is the rate of expansion, and that is the magic of Einstein. H comes from GR, and H is basically related to the stress energy tensor, and that is nothing but rho. And rho we calculated from like that. Is it clear now?
Yes, sir.
Clear? So this can be an examination question. I can tell you, I have a system where I have this particle, a fermion, and this particle, a boson. I have these degrees of freedom, calculate the expansion rate. Okay? And you should be able to calculate A dot by S squared. The rate universe is expanding that time. Okay? That is H. And once you know H, then you also know how to use that equation, gamma equals to H, the Friese-Wood equation. Okay, so now I'll be going a little bit deeper. So for that, I'll just keep the first line here. So now I just tell you, this I have done when they have the same temperature. But if they have different temperature, different particle, but still they are in Bose-Einstein or Fermi-Dirac. So it can happen like that, I'll tell you. So it is like that. Okay, I'll tell you a little later. Now let me do one thing. So what happens? First, your G star is very high. All the particles, G star comes from all particles. And it is your homework to find when all particles are in thermal equilibrium in standard model of particle physics. Means all fundamental, what is the G star? It is there in many books. It will be somehow around 100, 105 or 110. So you should find out. That is your homework, around 100. Okay. Now you calculated it is 10.75 when only neutrino and positron and electrons are in thermal equilibrium. So 100 say, then some particle goes out of equilibrium, then you have to, G star will go down or it will increase. If more and more particles keep going out of equilibrium, which will be the answer? As temperature drops, more particle will hit this M is equal to T, heavy particle. So heavy particle will go out of equilibrium, they become non-relativistic. So every time they become non-relativistic, the G star will go up or go down?
Go down.
Go down, yes. G star will go down step by. So J star will be like this. It is not a smooth function. It starts with 100, then suddenly it drops because maybe one or two particle goes out, quark and anti-quark. There will be a drop of 4, or all 6 quark goes. So there will be a drop of 6 into 2 into 2 because each quark has quark and anti-quark. So 24 drops like that. So universe thermal history is like that. Some step function, and every time some particle has gone out of the equilibrium. So it is saying that the universe is a hot soup plasma given in Big Bang, and as the universe cools down, different particles say, Tata, goodbye. Now I'll go to my home. You guys continue playing. And that is what happened. And today, and as today we'll see what is the value of G star. That we'll calculate soon. Today, what is the value of G star? Because that goes, if you know today what is G star, that or during CMB time what is G star, we need to calculate the H Hubble rate in every time in the cosmology. So we need to know. So is it clear that there will be a step jump in G star and decrease?
Yes, sir.
Yes. This plot you should also find out from Colby and Turner book or any Google search. Change of G star in the universe, you will see every time. So first maybe the Higgs boson and quark, they are very heavy. Quark will go down, and then after quark, something happens that will be happening microsecond level. Then we know that when universe is 1 second, then neutrino decouples. Neutrino is the only particle, their mass is very, very low, but they decouple at a very high. So neutrino is the only particle, they decouple because at a temperature when m nu is much, much less than T, because mass of the neutrino is almost like zero, photon ka jaise. But still they decoupled at, Jahang has done the homework, it is around MeV. Jahang, yes, right?
Yes, sir. 1 MeV.
So this happens because for other particle decouples happens when m is greater than T, or m is, I just said, around 10 times T for dark matter or quark or electron, positron, something like that. For neutrino, it has happened because it just happened because we did the calculation because of the nature of the Fermi constants, G square, T square. That interaction rate of neutrino is so low, gamma, that's why it happened early somehow. If you have more interaction, you stay in equilibrium for longer. Okay, that we know from last class. So more interaction means you stay at late time in the internet because you have to dilute more for Hubble. To suppose if your voice is more louder, means you interact louderly, then you have to separate even further not to hear each other, isn't it? Yes. Yes.
Yes, sir.
So Hubble has to expand even more to dilute their number density so that in your university building, it's just an example, you don't able to hear each other. But for someone who talks very lightly, even if you are separate on the other room, then you will not be able to hear each other. Clear? Yes? So you will be coming out of thermal equilibrium faster if your interaction rate is low. And that's what happened with neutrino. So now we're going to do something amazing. That what happens after, see, when they're in thermal equilibrium, then we know what is their distribution function. But now the question is, what happened to f of p, distribution function, after freeze out? Freeze out. This freeze out means it is the same thing called decoupling. You got the question? What we are now up to? Yes? Because f of p is always for thermal. So, but what happens after the decoupling, if I want to calculate their number density, if I want to calculate their energy density, then you also still need an f of p, right? Yes or no?
Yes, sir.
And so now let us go back. I'll do a new thing today. So, yes. Okay. Let me share the screen. This is very important for. So this is your homework. Forget about decoupling everything. From thermodynamics, you know that this is a note I'll give you, but you have to rederive it at your notebook. That TdS is this for entropy, and this double derivative has to be satisfied for integrating condition. Using that, you will find out that entropy ds is equal to d of rho plus p times v by t for a thermodynamic system. And when we know that from our conservation equation, d rho v is equal to minus p dv, so the inside term actually vanishes. Okay, d means not inside, sorry, wrong. The d of this whole thing vanishes. If you separate out the integral, the differentiate separately, then you use this d work done principle which we used before, then you will show that ds is equal to 0. That means entropy is conserved, and entropy is nothing but rho plus p times v by t. This is a thermodynamic thing, nothing to do with cosmology. So this is your homework. Is it clear? I'll give you the note, but you have to do it. Okay, a little bit more details. Okay, clear? So now we know what is rho, what is p, what is as a function of temperature from that integral I just showed you from Bose-Einstein or Fermi-Dirac. Okay. Now, in cosmology, sometimes we define entropy density, which is nothing but capital S by V, which is called as small s, called entropy density. Is S by V is nothing but rho plus P by T. So now you see, for example, say let's do it for a photon. So for photon, entropy will be, see, rho plus P. You can go back to the previous thing, which I am not going back now. Pi square by 30, and P will pick up 1/3 rho term. See, that's why 1 plus 1/3 G star, and both goes as T to the power 4. The T to the power 4 by T is T cube, so G star. So you get this term 2 pi square by 45 G star T cube. This will be the entropy density of photon. Okay. So now what is constant or any system entropy? So what is conserved is not T cube, is G star times T cube is conserved. Is it clear? Yeah, because entropy is conserved. Now, for example, now for say that there is no reaction is freezing out or decoupling is not happening, means nothing dramatic happening, that Hubble overcoming any reaction at a certain time. So when G star is not changing, then S goes as T cube. So now let us come here. So S, capital S goes as T cube times A cube, because capital is nothing but entropy density times volume. Clear? Yes? Hello? Because now I'm changing from small s to capital S. I'm small s ke liye I have divided by V. So I multiply it by V now, because what is conserved is not the small s, what is conserved is actually the capital S. Okay? Yes. So what is conserved? Entropy, not the entropy density. So G square T cube A cube is constant. Now if G star is not changing, for example, if I am on that plateau, G star does not change all the time like a monotonically decreasing function. G star changes as a step function. I have shown you from the picture. Here, draw car by draw. Yes? Yes? So when G star is not changing, that is the most of the time. Only G star changes in few points in the universe when some particles become non-relativistic or decoupling happen. Then T is, this is constant, so T is G star times 1 by square root 1 minus 1 by 3 A. And if G star is not changing at a point in that plateau, then T goes as 1 by A. So now I proved today that I was telling you that temperature actually goes as 1 by scale factor. Now it is proved from entropy. Clear? Any question?
Sir, G star won't change when there is no difference in the number, right?
This will not change. For I'll show you this will. So G star can only change in certain point. Tuck here, then tuck, then here, tuck. But in this plateau, when nothing is happening, means no particle is going out of thermal equilibrium, then G star is not changing, right?
Okay, sir. Okay, yeah.
So that's why this that's why this T goes. That is my next point. T goes as 1 by A is only true in this plateau here or here or here. In this junction, when the theta function is dropping, step function jaise, that time T is not 1 by A because that time G star is changing, right?
Yes, sir.
Now that is my next question. You tell me, suppose I have this electron and positron interacting with photon. These are the three things interacting, okay? Nothing else, electron, positron, photon, at very low temperature. And then say now the temperature is, electron mass is how much? 0.5 MeV almost, yes? So for example, I take a temperature around say 1 MeV or 2 MeV, for example, or 1 MeV. Or let's say 0.7 MeV. So that time electrons are still interacting with photon because the mass is still higher than, the temperature is still higher than the mass. Yes? So for example, T is equal to 0.7 MeV, but then when T reach 0.5 MeV, then electron mass start going below the temperature. Then what will happen? Electron and positron will say goodbye. Okay? They will separate out. So only photon will be remaining. And that was the case is actually for during CMB, only photon is in thermal equilibrium. Everything has fallen out. That's why when you see the cosmic microwave background, only thing is in thermal equilibrium, that egg-like 2D picture of blue-red spots of thermal equilibrium of 2.7 Kelvin is only thing which left remain in thermal equilibrium is photon. Neutrino could be, but neutrino is very light like photon, almost massless, but because of its so weak interaction, it has said goodbye at 1 second of the universe. When universe is around 1.5 MeV or something like that, 1 MeV. So only thing left, so if I start from below, around CMB, only thing left in thermal equilibrium is photon, and it is still today. So this is photon. Even today they are in thermal equilibrium, even today. When you see with cosmic antenna, that's what the Nobel Prize they got. It's in thermal equilibrium, Planck distribution. And then if you go above MeV, 0.5 MeV, then what more particle were in thermal equilibrium? Who can tell me? This reaction. E plus, photon, positron, photon, and electron. Is it clear?
Yes, sir.
Because below 0.5 MeV, the electron and positron cannot go to, this process cannot happen. Thermal equilibrium, you have to go both forward and backward equal rate. But gamma cannot create electron and positron because gamma has only temperature access. Gamma has no mass. But the temperature drops below mass of the electron. So how can you conserve the energy? So you cannot do that. So when it is hitting 0.5 MeV, then so this thing happens. Only photon is in thermal equilibrium. That is temperature is equal to 0.5 MeV and below. Above that, photon has company with electron and positron. Then little bit above that, around 1 MeV, that Jahan has done the homework. Then 3 neutrinos were also together with this. And if you go GeV, then you get quark and anti-quark, or you up and down. So the more and more and go up you go, the G star will become up and up. That's why you see this is up basically, high temperature, and this is low temperature, low temperature. Today is low temperature. So if you go in the left, you go to a very high thing, and that is maybe 100. That is your homework. Is it clear now? Thermal history of the universe? Yes?
Yes, sir.
Now, for example, this is now for you just to take a test. So this is, I'm telling, this temperature is, say, I'm plotting. Sorry, this is G star. G star. This is my temperature, 0.5 MeV. So now, for example, this is the G star. It was how much? You just said, no, you calculated around 10.75, isn't it? Before?
Yes.
Then what will be the drop? Drop to 2 only, because only photon will remain. Oh, sorry, wrong. Sorry. This is, I have calculated the neutrinos in it. Sorry. This is wrong. See, neutrinos has already come out of thermal equilibrium at 1 second, okay? So what is G star now? Only from only from electron, positron, and photon. What will be the G star? For photon, it will be 2, and for electron and positron, it will be 7 by 8, 2 plus 2. One for electron, another for positron. Yes? 5 point? So can you tell me the exact number without decimal? I just want to tell you, the not the point, just the fraction. How much it is? 4. So 7 by 11 by 2. Very nice. Everybody got it? I want to know. This is a very important thing we are going to do now. 11 by 2, and at 0.5 MeV, it comes to 2. Yes?
Yes, sir.
Clear for everybody?
Yes, sir.
Okay, very nice. So now, at this junction, 0.5 MeV, what happens? You see, what is conserved is, I just said, G star, the total, times T cube times A cube is constant. You remember? Yes? It is constant for all the time. Now, if you take this line, sharp this line, that means it is at some temperature T, or it is one point in cosmos, when almost sharp line when this decoupling happened. So for this line, A has a constant value. So when T is equal to 0.5, A will also have some value, say A star. Clear? Because that moment universe has some scale factor, right? Because T is going as 1 by A, but for a given T, A is constant, right?
Yes, sir.
Because A changes when you wait in time, but for a slice of time, A is constant. A is a number, isn't it?
Yes.
So that's what I'm in that slice. Now I'm matching in the left side G star, and then right side I have dropped G star to 2. Here G star is 11 by 2. So now you tell me, for this line, I can take A to be constant on both the cases, because this is almost like an instantaneous process. So G star initial before the freeze out times T initial cube is G star after freeze out final, right side, times T final cube. I'm matching this because A is constant on the line. So my T final of the same T final means the photon temperature. Now only thing remaining in equilibrium is photon. That is nothing but photon. Will be how much? G I by GF star to the power there will be a 1/3 factor times T gamma I. Means there will be an increase or decrease in temperature of electron, of photon. Who can tell me at this point? See, G star is decreasing, final G star is less or more? Hello? Decrease. So TF has to increase. So there will be a sudden jump in photon temperature. And that is by how much? 11/2 by another 2. GF is finally 2. So 11/4 to the power 1/3. So T photon will get a jump when electron and positron goes out of equilibrium by a factor of T photon before freeze out, and this is after freeze out. Is it clear? This is very important, and it will be very important very soon in the next 10 minutes. But anybody had any question here? So every time there is a drop in G star, there will be a kick in temperature, whomever remains in the equilibrium. It is like that, कोई दोस्त का बीच में fight होता है तो hey, I am leaving you, but जाने का पहले they give their entropy, high entropy fight to the people and then they leave, isn't it? Yes. So like that, here also entropy is conserved. That means the entropy of the electron and positron, they are now going out of equilibrium, so they give their entropy to the G star, to the photon, and when you get more entropy, your temperature increases. Clear? Yes. Because this equation is coming from entropy conservation, right?
So it's like from a system, when some particles leave, the energy of the system is increasing.
Sorry?
It's like from a system, in equilibrium, when some particles leave, the energy of the system is increasing.
Exactly. Basically, it gives their entropy to the system and then go, because entropy has to be conserved. Okay?
Okay.
So now, remember this is very important. Now I'll go to a little bit different topic, but I'll connect back with this for a very important thing. Is it clear for everybody now?
Yes, sir.
Very nice. So now let us now go to this. So this I have now done. Okay, and so now the question is this one. What happens to the distribution function here? How do the distribution function change of a decoupled particle, or they evolve once they decouple and thus fall out of thermal equilibrium? So the answer to this is, I'm reading it out from the note. Their evolution can be obtained from the fact that after decoupling, a species evolves without interacting, and therefore its distribution function dn by d cube p, that is the definition, is conserved because it does not interact. That is the Liouville theorem. Then we know that n, the number density falls as 1 by a cube. We have done it again and again and again because it goes as 1 by v goes as a cube. So a to the power minus 3. Thus, for f to be conserved, if n goes as 1 by a cube and here is a triple power of p, p also has to go as 1 by a to conserve the f of pt. Because n goes as 1 by a cube, so if p has to go as 1 by a cube, then only it can be conserved. Otherwise, it cannot be conserved. So now this form, p goes as 1 by a. It's also very similar when they were in thermal equilibrium. I proved there also p goes as 1 by a, right? Yes? Oh no, sorry, I did not prove. Sorry, wrong. I proved t goes as 1 by a. I am yet to prove. So now what I am going to do, that P goes at 1 by A. So now let us write the distribution function f of pt just when they were in equilibrium, before decoupling, just at the edge. After that, they will be decoupling. So what is their decoupling function? So I will actually, let me derive it, otherwise you will not be able to understand by reading the note. Though it's very simple, but it's not so simple. Let me go. I just, whatever I told, I'll derive it. So now I tell you that from Lebesgue's theorem, f of p t is conserved and pt is dn by dqp, means in a momentum volume, what is the number density? That is the f of p in a unit volume of momentum. And we know that n goes as how much? 1 by
A cube.
So that means if this has to be conserved, that means it does not depend on a scale factor, then p has to also go as 1 by a, because it is p cube. Okay, the dimension is, so p has to go as 1 by a, because this is the to the power 4 of p. Okay, to the power 3 of p. Okay. So is it clear now? P has to go as 1 by a. Hello?
Yes, sir. Yes.
Ah. Now it is basically momentum of each particle after decoupling. After decoupling. So basically what is happening, say this was the distribution function, as I say, around Planck distribution at the time of decoupling, but now this is their momentum p and this is their number density. Okay, now what will happen, I'll tell you how the distribution function will look after the decoupling. That is my question. So now remember this one, p goes as 1 by a. So if p goes up at 1 by a, then a times p is constant. So that means a decoupling or freeze out times p decoupling is equal to after a is normal, because a is going down and they have a momentum p. Okay, ap. This is after and this is before. And this a is any number, p is any number. Now let me write down the distribution function. What is the distribution function at decoupling? Can somebody tell me? Distribution function at decoupling will be f of p decoupling and a time. Now from here, p decoupling is nothing but a, which is function of time or temperature, also time times p. I'm writing p at the later time, because they will evolve as the universe is expanding, divided by p decoupling. Sorry. It will be a decoupling. Is it clear? I'm just doing side change. I'm writing p decoupling as a function of at later time a and later time p divided by a decoupling by using, because I know that a decoupling p, because I'm using p times a is equal to constant. Clear?
Yes, sir.
Yes, sir.
So now if I substitute it here, it will be how much? F of p decoupling will be the momentum at a given time pt by a at a given time by a decoupling. I'm just substituting this and then function of time. So you see, now what I am going to do, define a new temperature T, or new temperature nahi chahiye to I am with the P. Okay, and P is okay. So now let me write down the distribution function. Okay, so you remember the distribution function is sorry, so many things. I'm writing down the distribution function exactly. You remember it was very simple: P by T plus minus 1. Remember?
Yes, sir.
Because KB is equal to 1, and mu we neglected the chemical the mu E minus mu, no? So mu is much less than E, and P E equals to PC at relativistic most of the cases. I'm doing it for the neutrino mainly now. So E equals to PC. So this one is, so neutrino it will be plus or minus?
Plus.
Okay. So now, if I substitute my distribution function, this is the form. Okay. So what if I substitute this? I am not going to the next page because I want to see the result. I am using this here. Now here I am using, it is f of, at a later time, it will be still a function of P, but with a redefined thing. So it will be 1 by e to the power. Okay, sorry. This is the decoupling. Sorry, e to the power decoupling. Actually, let me go to the notes because here it is getting complicated. You will because I am not following the chronology, but you will understand now if I go to the note. So now see. So I am writing f of equilibrium at a later temperature and later P is PT A by A decoupling times T decoupling. This will be the same thing, 1 by e to the power this. I am now substituting PT as, see, the form of distribution function is P times A by A decoupling divided by T. Is it clear? Because now my new P has become P times A by A decoupling. I have been deriving it. Clear?
Yes, sir.
Because P is at a later temperature, later times, and divided by T decoupling. Here you can see, and then this. So now I define a new temperature T, which is T decoupling times A decoupling by A. Here I'm defining. So then it will again come in the form e to the power P by this capital T, where my new temperature is T decoupling times A by A decoupling, and it also falls as 1 by A. So though it has gone out of equilibrium, but as momentum distribution is conserved, here also it follows the same distribution function, though they are not in thermal equilibrium, and the temperature goes as 1 by A, which is exactly case for photon also, for neutrino also, when they were in thermal equilibrium. So I'll explain it little bit in more detail. This is very important. So now here, okay, let me erase the upper part. I'll use this part for explaining you in more detail what it is in the note, but I think it will be good to say it again and what I told in the note. You got it, or shall I say it again? Hello? Hello? Shall I say it again? So one thing, I have now derived P decoupling is A later times P later by A decoupling. So now let me write down the F at the time of decoupling, when the freeze out happened. It is nothing but 1 by e to the power p decoupling by t decoupling plus 1 for neutrino. I'm writing it for neutrino. Is it clear? Now you tell me, if I substitute the p decoupling from here, what I'll get? I'll use this equation, this one. So it will be p of t, that is my normal, like this p of t times A. I'm not writing A by A decoupling. I'm just writing A by decoupling, or I can write A of t. But still, there is something else by t decoupling. By t decoupling plus 1. Now, if I define this thing as some temperature T, new temperature after their decoupling in their own system, but do you see that the new temperature T, so this will not be T, basically this is 1 by T. Okay, so I define a new temperature T, which is T decoupling into A decoupling by AT. So with this new definition, what will be the new distribution function? Who can tell me this one? With my new temperature of the, I am calling it T prime. Okay, so what will be the new distribution function? 1 by e to by T prime plus 1. Very nice. And what is T prime? You see, T prime goes as decoupling temperature jo tha, whatever was decoupling, and it falls as 1 by A. Yes, 1 by scale factor, right?
Yes, sir.
So for photon, which has not been decoupled at 1 second, because photon, electron, positron, their temperature, how they go as 1 by I have
1 by A.
1 by AT. That is for even equilibrium people also who have not come out of the equilibrium, they also go as 1 by. So basically neutrino temperature, new temperature will also be actually very equal to the photon temperature. That's why I'll erase this T prime, because both of them falls as 1 by A from the T decoupling. So there is actually no change in temperature here. And also they keep the same distribution function as if they are in thermal equilibrium. Okay, so now think about it a little bit more. I have mathematically proved it, but you got intuitively, no? That I have used the decoupling distribution function, I have conserved it. But using the conservation, I have shown that it is very similar to P by T. I have been using this only. I have not taken any new distribution function. I have taken only the distribution function at decoupling, and from there, step by step, I have come to this new one. This I have not used a new distribution function. This one is just a step-by-step calculation of A decoupling, P decoupling is equal to A times P. I have substituted and redefined a new temperature T prime, and then later I say that T prime is nothing but T, because it also goes as 1 by A. And at equilibrium, they had the same temperature. Now it is almost like two friends separates, but both of them, suppose their temperature falls as 1 by A. So that means they will keep in the same temperature, right? Yes?
Yes, sir. But the temperature is kind of scaled, right? By the decoupling temperature and the scale factor.
So that's why equilibrium distribution function is conserved, but still here see there is no different dependence on A, but here I have used this form. P decoupling is equal to this. And this has come from my, I have proved it already today. And when I substitute it back, I get a temperature different. I get a new temperature definition which goes as 1 by A. So I am getting a similar Bose-Einstein, a similar Fermi-Dirac distribution with a temperature T, where my new temperature T prime is T decoupling times A by AT. So this AT factor is coming when you want to match it with a Fermi-Dirac distribution. So if you want to say that my new distribution function is actually a new Fermi-Dirac distribution, even if they are in not thermal equilibrium, but they are Fermi-Dirac distribution with a new temperature T prime, but then I see T prime goes as 1 by A from here. So then I say, okay, that means it will continue in a thermal, not in a thermal equilibrium. It will be having same distribution function, but with a temperature scaled as 1 by A. Which you are right, temperature will scale as 1 by A. So think about it, Jahan, because read it in many books, because this is itself is a very deep thing about thermodynamics of decoupled particle. You should not expect to understand everything in 5-10 minutes. Okay? Shall we all read it in the weekend? Yes?
Yes, sir.
But I gave you the all mathematics. Now you have to swallow it inside your body and mind like that. Take pen and paper and do it again, and then you will know. So now what is happening? Here at 1 second, you have electron, positron, other things and 3 neutrinos and photon. And then neutrinos say goodbye. 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 3 neutrinos. Nu, E, nu, mu, and nu, tau. They are the 3 neutrinos. Okay? 1 second. So then, what happens? Neutrinos separate out nu, E, nu, mu, and nu, tau. They are in their own sector. And here you have E plus, E minus, and photon. But both of them, temperature goes as 1 by A. Here, temperature goes as 1 by A. Clear?
Yes, sir.
Now, so even if they are in thermal equilibrium out, both cases, if you wait for a little bit more time, you will see neutrino temperature, T nu, and the neutrino photon temperature, they will be same. But they are not talking to each other. They are not in thermal equilibrium. But this is just happening. I proved it. Clear? Okay? But then one magic happens. Sorry. Then the magic happens. Then the magic happens at T equals to 0.5 MeV. What is the magic? In the left side, I have just said the neutrino, the photon temperature will have a kick in the last slide because of the electron and positron gives their entropy. So photon temperature will have increased by how much? Who can remember?
Cube root of 11 by
11 by 4 to the power 1/3. And because of the entropy transfer. But as neutrino are not in thermal equilibrium, the electron and positron will not be able to give their entropy to neutrino. Clear?
yes, sir.
So the neutrino temperature will not change. But here you get a kick of 11 by 4. So from now point onwards, if you match match photon and neutrino temperature, will they be same?
No, sir.
No. So what will happen? Photon temperature. So this happens around 0.5 MeV. Now, for example, CMB happens around 0.1 electron volt. I proved it, kind of said it. A little bit less than 13.6 electron volt because of the distribution function tail of high energy. So at CMB time, if you see, what will be the photon temperature compared to neutrino temperature? Just this factor. Clear? because there is no more entropy change after that point, because then photons remain alone. So then their temperature still goes as 1 by A, and here again it goes as 1 by A. But here you get a kick. So that's why you get a kick of 11 by 4. So today, that's why in cosmic neutrino background is at a lower temperature, photon is at this. And if you do that, then you know photon temperature is this. So neutrino temperature, can you check it? Is it 1.9 Kelvin? It will be like 4 by 11 to the power 1/3. Can you check it in calculator? So T nu will be T gamma times 4 by 11 to the power 1/3. 4 by 11 to the power 3rd. I am side changing. And you put the value of 2.7. How much you get? Can you tell me? The neutrino today? Tell me when done. Got it? It's just the arithmetic, no? Calculator. I'm just asking you to calculate the photon neutrino temperature today by 4 by 11 to the power 3. How much?
Yes, sir, it's 1.95.
1.9. Take I know this number 1.9, no?
Yes, sir.
Okay. So that's why today we derived why neutrinos are a little bit lower than photon temperature. Once we discover cosmic neutrino background, it will be discovered in 10 years. You will see that it's still in radio wave, but its temperature will be little less than photon temperature. And that's the amazing thing about thermodynamics, particle physics, electron, positron, and all these things. Okay? Annihilation, and that's it. So this much is more than digestible for today. A lot of new things we are doing. Okay. And so this is what it is. And where it is, let me go back. Yeah, this is what the proof. 1 point G star this. I'll send you the notes. And you see we have all done it. The G star was 11 by 2. Later it is 2. So it is that. So the ratio is 1.4. So it is 1.9 Kelvin today. Okay. So now, final thing. Today, suppose in CMB time, during CMB time, you want to calculate the total energy density of the universe because that will determine the Hubble rate. So it will be pi star by 30 G star times T to the power 4. But now, as T neutrinos are little bit different than T photon, so you cannot take in the bracket naively. You can take in the bracket, but then you have to take a 4 by 11 to the power this factor. Is it clear or not clear? Not clear? Shall I do it? So what is rho CMB? So it is pi square by 30 into G of photon times T to the power 4. This is G gamma plus pi square by 37 by 8 into G neutrino times T neutrino to the power 4, because now it is not the same temperature. Now I have to write T photon. Is it clear?
Yes.
So now let us do something. Pi square by 30, I take it common out. And I still define a G star. And I say, this is I take it out as photon temperature. So now if I do it, then this will be photon temperature. The G gamma is 2. Now if I take in photon temperature out, so there will be no photon temperature term. So 7 by 8. Pi square by 30 will not come. I have taken it out. What is G neutrino? 6. Yes? 3 times 2. Correct? But as I have taken T photon out, so I have to T photon out to the power 4, there will be a factor of T neutrino by T photon to the power 4. Is it clear? Just a simple mathematics. So what will be my G star now? 2 plus 7 by 8 times 6 times T neutrino by T gamma. We now know what it is. It is 4 by 11 to the power 1/3, but there will be a 4 factor here, so it will be 4/3. So that will be my G star during CMB. How much it is? Can you calculate?
Uh, 3.36.
3.36. G star is 3.36. So it will be 3.36 into pi square by 30 into T to the power 4, the total energy rho. This has been proved by Planck experiment. So that means it is true that neutrino temperature is in 4 by 11 to the power this. They have calculated exactly the rho of radiation, because neutrino is still behaving like radiation, because it still has a thermal distribution, though it is non-relativistic, though it is as a decoupled. Sorry. Okay, so this much enough for today, and that has been amazing that has been proved by Planck. Okay, so this is the thing. 3.36, you are right, 3.36. Okay, and then you know what is rho r, and if you put here, it goes as you know that I will not do that. It goes as rho goes as T to the power 4. Okay, so this T to the power 4, but T can go as 1 by A. So 1 by A to the power 4, and A goes as 1 plus Z, 1 by 1 plus Z. So it will be going like 1 plus Z to the power 4. So now as you wait, as you come to lower and redshift, it happens at 1100, Z is equal to CMB. Today you are at Z is equal to 1. So it will be, the temperature that time was pretty, today it is, if it is 2.7 Kelvin today, that means that time it is 1 plus Z to the power 4. So 1100 to the power 4 more. So find out the temperature, 2.7 times temperature of CMB at the time they were released was actually 2.7 times 1 plus Z. So it will be 1100 times 2.7 Kelvin. We have done it before. Okay. That is simple. Okay, very nice. So this much is enough for today. Clear?
Yes, sir.
So lot of mathematics, lot of concepts we have done today. Okay, so officially it ends the cosmology class, but the next class I'll take on the dark matter. It's very fascinating. I'll show you some of the movie and some of the searches of dark matter under the mind, and we can take one more class. We can still include in the exam that one because we are running late. Depending on you, because that class will have less mathematics but more slides, movie, and all these things. Is it clear? Okay.
Yes, sir.
So now it is our ritual time. So say bye till Monday. Okay. So let's turn on the video. Good. So it was helpful today. Yes. Lot of new concepts. Ravi, it was also helpful for you.
Yes, sir. Sir, I have one question. So, at the time when the photon decoupled from the electron and positron from them, so they get energy enhanced like the factor 11 by 4 now. So, at the time when the neutrino decoupled, so then the entropy conservation did not happen like that time.
But even if it is a very good question, because when neutrino decouple, that time the entropy of the other thing means the amount of entropy neutrino give to the whole fluid is much less compared to the whole entropy. So it will be a very tiny change. It's 1 part in 10 to the power 10 or 20 because neutrino did not carry enough entropy. Okay, so because there are many particles that time, but it is true there will be a little bit jump of G star, but still one thing is true. Even if there is a jump, see the electron, positron, and photon, all of them still share the new temperature. Yes, because they remain in equilibrium.
I didn't get.
No, I just said that when you come out of equilibrium, neutrino did not here when electron and positron goes to photon, decoupling happen. The kick in temperature that time for both electron. I did not. That's why I never used the idea that electron positron has a lower temperature. Getting the point?
Yes.
So decoupling does not change the temperature. That's why I have used that T decoupling is when decoupling happen. Suppose I am talking with Jahan and I say like now bye. We have a fight, temperature increase, but now both me and Jahan temperature are same. We are not so we have never used that electron and positron temperature was lower. No, when even the decoupling happened, both electron, positron, and all the photon got heated up. But then they decouple. Entropy was going down. So that's why does it answer your question that the neutrino actually does not go down in temperature or rise up during neutrino decoupling?
No, but the same thing should be applied for that in a photon also.
Which one?
Isn't it same? What is the difference between both cases? Then it will be clear. Like when the photon decoupled and when the neutrino decoupled, how is they are different? Like in one time they are getting energy, one time.
Photon did not decouple. The electron positron decoupled.
Yes. So they gave the energy to photon.
Exactly. So that's the idea. Okay. But there was nobody to give energy to neutrino. Is it clear now? Because neutrino has already separated out. Okay? Yes?
Yes.
Like think about it. It's like that. Okay? Okay, then we'll see you Monday. Yes? Yes? Yeah. Oh, sorry, not Monday, Wednesday. Okay, we'll do the dark matter. Okay. Okay, very good. And do the homework, what I told you, all of you today. Okay? Okay, very good.
Thank you, sir.